Okay, welcome to Class 3, Automata and Formal Languages. And today what we're going to do is we're going to look at a formal way of defining languages that's a little more powerful and a little bit kind of more precise than the way we've been doing it before. Now, quickly to review what we talked about previously, a language. A language is a set of strings over some alphabet. And an alphabet, if you remember, was really just a finite, non-empty set of symbols of some sort. And a string was a finite sequence of symbols over some alphabet. So in other words, a language is just a set of these sequences that are all over some chosen alphabet. And remember, that alphabet has to be finite, has to be non-empty. So in other words, every language has some defined finite non-empty alphabet associated with it, and every string that's in a language is going to be an element of that alphabet star. And remember, the star is 0 or more, so you're allowed to have strings that have no symbols in them, like the lambda, and you're allowed to have strings of 1, strings of 2, length 3, length 4, and any number, arbitrary length string in those languages. So a language itself could be finite, meaning it has some set finite number of strings in it, or it could have an infinite number of strings in it. There's no limitation on how many. And also a language could be empty. It doesn't have to have any strings in it. You could have a special language called the empty language, which it's still a set. It's just a set with nothing in it, would be the empty set, but that could still be considered the empty language, which is a language with no strings in it. All right, so that's what languages are. Now, that set of strings over some alphabet. Now, previously we had kind of defined these using a number of ways. We use set notation, where you just have curly braces and list the things out, separated by commas with ... We've used set formers to say all curly brace, all strings, such that, and then some description that defines that. We've also maybe used some English language descriptions. But the problem with all of those is that, like the set notation and set formers, is sometimes those could be unclear or difficult to use precisely, especially if you have a more complex language or pattern more complex pattern that defines that language. And an English language description of it is also equally problematic in that it can be ambiguous or unclear. So, for example, if I say that the language that I'm thinking of is all strings with consisting of exactly, or strings that contain exactly one B. Well, what does that mean, containing exactly one B? That part is pretty clear. But are there other things besides the B, or is it just the one B? What are those other things? Does the B have to be at the beginning? There are a whole lot of things there that don't show up in that sentence that need to be understood. And so we don't want people to make assumptions and get the wrong language. We want to have a very precise, very well-structured way of defining those sets of strings. And so that's what we're going to look at today, is this formal method that is much more structured, much more precise, easier to understand, and avoids the kind of lack of clarity and the ambiguity associated with an English language description or set notation and set formers. Okay, so that methodology is called a regular expression. And regular expressions are kind of this formal method of defining a language, a lot like algebraic expressions are a formal way of kind of encoding or defining a mathematical relationship between items in an algebraic expression. So each regular expression defines some language, and we would write that as the regular expression R, whatever it happens to be, defines the language that's kind of that regular expression R. So in other words, these are kind of saying the same thing. The regular expression by itself is representing the same language as the language that's embodied by that regular expression R. Now, the way we form regular expressions is very similar to like algebraic expressions, that we basically can use operators to create more complex regular expressions from simpler ones and define increasingly complex the expressions that each will define a language. So again, very much like algebra. In algebra, you have like a algebraic expression like mx plus b, or 10x plus 5, like the equation for a line. So with that, there are operators there like the multiply, like the plus, and there are also variables like the x, and there are parts of it like the 10 and the 5, which are numbers. Those are all kind of components stuck together with operators. We're going to do the same thing, but we're going to do that to define languages with these regular expressions rather than algebraic expressions. Okay, so let's take a look at that. So formally, there are kind of two types of regular expression. The first type is the primitive expressions. Those are kind of the basis set, or the base set of expressions. So equating this with like an algebraic expression, that would be like the numbers or the variables in an algebraic expression. 5x plus b, that would be like the 5. That would be like the x. That would be like the b. So those are the kind of lowest level components of it that there are. Now the composite regular expressions, those are created by combining other regular expressions using operators. A lot like in algebra, you have the arithmetic expressions like exponentiation and parentheses and multiply and divide and multiply and subtract and so forth. All right, so let's start off with the primitive regular expressions. There are 3 of them that are defined. The first one is lambda. So regular expression of lambda is a regular expression that defines the language consisting of just lambda. So in other words, this is a language that has one string that happens to be the empty string, the string with no symbols in it. The next one is this empty set symbol, the null symbol, and that's a regular expression that defines the language, the empty language. This is a language with no strings in it. So there are no elements in this set. Notice that these are different. This has one string, which happens to have no symbols in it. This has no strings at all, not even the empty string. This is called the null language. And then we have another one. We say if A is some element of our alphabet, then A itself is a regular expression that defines a language consisting of just that symbol A. And this is not just saying it's always A. This could be B or C or 1 or 0, or any symbol that's in our alphabet is itself a regular expression that defines just that symbol, a language consisting of a string of length 1 that is just that symbol. Now that we have our base regular expressions, we can combine those using operators. So what do the operators look like for the composite expressions? Well, there are 5 of those. And the 5 of those are listed here in these bullet points. So the first one is, and let's kind of get the rules here, that we're saying if I have 2 regular expressions, R and S, and each of those define their own language, the language of R and the language of S, then we can make a new regular expression by saying R and then this vertical bar symbol, like the pipe symbol, S, and this is called the union operator. So R vertical bar S, or R union S, is itself a new regular expression that defines the language of R union language of S. And when I read this, I might say R union S, or I might say R or S, because that's kind of what union means, is the string is either in this or it's in that. It's kind of in the collective set of both of those, one or the other, or both. So I might say R or S when I read that. But R vertical bar S is essentially the union operator, and that itself becomes a regular expression as long as the 2 parts are regular expressions. Now the next one is concatenation. RS, we just stick them next to each other, just like 5x plus b. 5 and x are just kind of stuck together. So if we have a regular expression stuck onto another one, that defines concatenation, and that means, or that itself as a regular expression defining the language of R concatenated with language S. And as a brief kind of review of what concatenating to language means, that means that the RS means we're creating the set of all strings where the first part is defined by this language R and the second part is defined by the language S. The next one is the star closure. So R star is itself a regular expression that defines the language R star. So in other words, this is 0 or more iterations of R concatenated with itself. So 0 will give me lambda. So in other words, this is like lambda union with R, union with RR, union with RRR, union with RRRRR, union with all the way up to an infinite number of them concatenated. So this is repeating this language or concatenating with itself 0 or more times. The plus operator is a regular expression. So any regular expression plus is itself a regular expression that defines the language LR plus, and that's just 1 or more. So the same thing as star, but 1 or more repetitions of it. And then a regular expression in parentheses is just the language R. It does not change the meaning of the language. So parentheses are used for grouping. Just like in algebra, if you put the number 1 in parentheses, it has the same value as the number 1. If you put a 1 plus 5 in parentheses in algebra, it still means the same mathematical thing as 1 plus 5. So parentheses are just for grouping. Now, speaking of grouping, why would we need to group things? Well, the advantage of that is because there's a precedence, just like there's a precedence in algebra. If you remember back to that PEMDAS kind of mnemonic that a lot of people seem to learn in algebra for the order of operations, the same thing is true for this, that parentheses are at the top. That's the highest level of precedence, followed by the plus and the star from left to right. And notice that that's kind of the equivalent of exponentiation, followed by concatenation, which you can think of as the equivalent of multiplication, followed by the union operator, which is the equivalent of addition. So in other words, this kind of goes parentheses, star and plus from left to right, concatenation from left to right, and then union from left to right. So they have their own built-in order of operations. So given that, we now have this methodology by which we can formally define languages. Now, one quick thing that I want to point out before we go too much further, there are some languages that we cannot make regular expressions for. In other words, this methodology for defining these patterns can define a whole lot of languages. In fact, there's an infinite number it can define, but there's some that it can't do. And the family of languages that it can define are called the regular languages, which is why this is called regular expressions. And don't worry too much about that right now. We'll come back to like what does it mean to be a regular language, and what are some languages that we cannot define with regular expressions that are not regular languages. We'll come back to that in a later class. But right now, just note there are limitations to it. Okay, let's look at some examples. So we're going to go through just a few examples here. The first one here, A union B. So A, if you remember that, that's a primitive, and that defines the language of just the set containing just A. And this one defines the set containing just B. So if we union the A and the B sets together, we get a set containing both A and B. So in other words, looking at this is like A or B. Well, it's either an A or it's a B. And there's my answer for that. Now, let's look at another example. So here's another one where I took the A or B, put parentheses around it, which doesn't change it. So this is saying the set A comma B, that language, concatenated with that same language. So in other words, we have A comma B concatenated with A comma B. And remember, that's saying the first part of this string comes from this language, meaning it's going to be an A or B. And the second part comes from this language, which means the second part's going to be an A or B. So what our resulting language looks like, it looks like first part A, followed by second part A, first part A followed by second part B, first part B followed by A, B followed by B, and that's all the combinations we can have where the first part is either an A or B, second part is an A or B, so there's 2 here, there's 2 there, 2 times 2 is 4. We end up with 4 possibilities that come out of that. Now, notice the use of parentheses here though, and the reason we did that is because that forced the union to happen before we did the concatenation. Let's look at another example. Now this example is the same as the previous one, but I took the parentheses out. In other words, this is the same string. I just removed all the parentheses and I wind up with that. And notice that that changes the meaning because the order of operations says concatenation comes before union. So in other words, we do the B and the A first. So B concatenated with A is just B followed by A. And then we union that with A, which gives us just A, and B, which gives us just B. So we get B, or A, B, A, and B. And one thing to keep in mind is the order doesn't matter. You could have done A, comma, B, comma, B, A. It would be the same language that we have here. But notice that I kept it in this order to match the expression over here. But order doesn't matter. These are just sets. These are not sequences. So we could have listed these in any order we want. They're the same set. Okay, let's look at one that uses the star closure, star operator. So A star. So A is just the language containing just A, the set containing just this one character string A. And this says repeat it 0 or more times. So here's with 0 A's we get lambda. With 1 A we get just A. 2 we get AA. 3 we get AAA. 4 we get AAA. And so forth. And notice this one is infinite. The previous 3 were all finite. This one, however, infinite. So this is 0 or more of A. All right, now, A, B star. Now, remember the order of operations again, that precedence. The exponentiation happens before the concatenation. So in other words, this star goes with the B, not with AB. It goes just with the B. So this is saying all strings that start with an A and then continue on with 0 or more B's. So there's the A with 0 B's, here's with 1 B, here's with 2, here's with 3, here's with 4, and so forth. Again, another infinite language. And notice now I've added parentheses. So this is the same as the previous one, but I put parentheses around the A and the B. So that's forcing the concatenation to happen first, and then we're having 0 or more of that thing that's been concatenated. So in other words, this is saying 0 or more ABs. So there's 0 ABs, here's 1, here's 2, here's 3, here's 4, and then so forth up to an infinite number. So notice the parentheses here are forcing the concatenation to happen before the exponentiation. Where up here, the concatenation happened after the exponentiation. All right, the next one, notice this one is similar, but I put that union operator between the A and the B. So this is saying A union B, that whole thing star. So A union B, we had that on 1 up here. That's just A comma B. So that's 0 or more of this language up here concatenated with itself. So there's 0. Here it is raised to the first power. It's just an A or B. Here it is raised to the second. All strings of 2. So in other words, this is all strings of A's and B's that are either 0 characters long, or 1, or 2, or 3, or 4, and so forth. Okay, notice this would go on with 4 characters long, and 5 characters long, and 6 all the way up to an infinite number. And you might notice by now that anything that has the star or the plus, at least so far, the star is going to create an infinite length. The plus is also. That doesn't mean you couldn't have some regular expressions that have a star and plus that still make something finite, because you could have something with the empty language in that. We'll talk more about that later. But for the most part, when you see a star, you're saying take this thing and repeat it 0 or more times, and that more means an infinite number of times, which makes infinite languages. All right, the next one, A or B star. Notice this is the same as the previous one, but I took out the parentheses. So this is saying it's either an A or it's 0 or more B's. So here's just the A, and there's 0 B's, there's 1 B, there's 2, there's 3, there's 4, there's 5. So it's going to be lambda. That comes from B star. The A comes from there. The 1B, 2B's, 3B's, 4B's, and so forth. And again, the order doesn't matter. It might have been more clear if I said A, comma, lambda, comma, B, comma, but I kind of put it in this order to start with the shortest string first, the string of length 0 first, and then 1, and then 2, and then 3, and then 4, and so forth. So we either have a single A, or we have 0 or more B's. Now this one, this final one on the list here, That one is a little bit complicated to list out the elements of. And this kind of illustrates the power of regular expressions here, I think, because if you tried to list all of these out, notice I have 1 or more A's followed by 0 or more B's followed by 1 or more A's. And notice if I tried to list those out, well, maybe the first one would be like A, because A, no B's, and an A. But then what would the next one be? A, or it would be A, B, A, because I could increase the number of A's here or there, or the number of B's inside here. And so there's not really an easy way to do this in the traditional notation with a dot, 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 because this can grow in length from 1 or more. The middle part between the two A's can grow in length from 0 or more. And the last part can grow in length. So how do I establish the pattern here when all 3 of these can kind of grow independently? And so this one's complicated to list, but you'll notice that looking at the description, or the regular expression here, the description would be 1 or more A's followed by 0 or more B's followed by 1 or more A's. But this regular expression captures all of that really succinctly and unambiguously and precisely, where it'd be hard to write out the elements with something like this and establish a pattern for it. And that's one of the powers of regular expressions, is this precise, compact, unambiguous nature of defining these patterns that define the language. Okay, so what I would suggest you do is take a close look at those, make sure you understand all of them. That's going to be important for doing your homework in this class. It's also going to be important for understanding where we're going to go moving forward in the future here. But one of the things that I want to turn you loose on here is looking at the lab assignment for this class, specifically on regular expressions. This is lab 1. So let's just switch over to the display and take a look at that for a second. And I'll just quickly go through the lab. So here's the lab. You notice it has a due date on it. And notice it consists of 3 parts, part 1, part 2, part 3. But really, you're doing the same thing in each of those parts. So looking at them, the first part, write regular expressions for the following languages over the alphabet, A, B, C. And then there are parts A through G on here for part 1. So let's just quickly kind of take a look at one of these here. Let's start with this first one. So all strings containing exactly 1 B. And you'll notice all strings containing exactly 1 B there. Let me switch PDF readers just quickly, and then so I can draw on this, because I don't think with Chrome I can. So hold on just 1 second here. And here, let me close that. Leave. All right, give me just 1 second, and then I'll reopen that. In a PDF reader where I can draw on it. Okay, so here we go. Let me zoom in on that a little bit. And now, let's go ahead and look at this first one. So I'm going to do the first one. So everybody should get at least one of these right. So I'm going to say draw. And on this first one, all strings containing exactly 1 B. Now, what does that actually mean? All strings containing exactly 1 B. Now, your first thought might be, and notice that the alphabet is A, B, and C. So your first thought might be, well, I'll just write a B, and that'll be my answer. So maybe something like that. But notice that that's not right, because it doesn't, while that contains exactly 1 B, that's not all strings that have exactly 1 B. So for example, AB has 1 B, or BA has 1 B, or BB does not. That one doesn't fit. That has 2 B's. But CB, or ACB, or ABC, notice there are really an infinite number of strings that contain exactly 1 B. So this is actually wrong. So don't do that. That's wrong. So the question is, well, how do you create all strings consisting of, and here, let me move that over a little bit. Let me erase that. Let me draw again. Let me put it over here. So B. So if you try to do that, that's not right. So how do we do that? So here's a way that I would think about it. We know that the string is going to have one B, but something could be before that B and something could be after that B. Now, what could be before it? Well, since it has to have exactly one B, the thing that could be before it can be anything that's in our alphabet as long as it doesn't have a B in it. So this would be a string of characters that is entirely composed of A's and C's. So how can we do that? Well, and it could be length 0. We don't have to have something before, but we could. So the first part about this is to maybe recognize that, hey, what's going to come before this can have 0 or more. So I'm going to put a star here. And I apologize, I'm drawing this with a touchpad, so it's kind of bad looking. And what's going to come after this could have 0 or more. That's supposed to be a star. So we have something star B, something star. Now what is this? This can be anything as long as it's not a B. Well, what is anything except a B that's part of our alphabet? This would be an A or C. And then after that would also be an A or C. So this would be an answer for part A. This will only ever produce strings that have exactly one B, and it could be any of them because we can have 0 more A's and C's before it and 0 more A's and C's after that. Now moving on to number 2 here, all strings with exactly 2 B's. Notice that the initial reaction might be, well, I'll just take the same thing, I'll just put B in the middle. But notice it doesn't say the B has to be right next to the other B. There could be something between those 2 B's. So I'll let you puzzle out how to do that. Notice that these are going to take a little bit of effort because notice it says your defined language, or the specified language, should work for any, all, and only those strings within the language. In other words, we can't have any that are left out. We can't have any extra ones that don't belong in the language. So when we get to this one down here where it says all strings with exactly one A and 2 B's, notice your thought might be to say, well, the A comes first, and then we have B and another B, but it doesn't say that. It just says there has to be one. If we count up the number of A's, it's going to be 1. And if we count up the number of B's, they're going to be 2. There are never going to be more than 1 A or less than 1 A. There's never going to be more than 2 B's or less than 2 B's, but it doesn't say they have to be in any specific order. So you could have the A between the 2 B's, or they at the end of the 2 B's, at the beginning. And also notice it doesn't say anything about the number of C's. So we have to have C's that can be anywhere in there as well. Same thing with this part E, all strings with at least one occurrence of each symbol of the alphabet. That means we have to have 1 A and 1 B and 1 C, but we don't know they're going to be what order they're going to be in. A could be first, or it could be in the middle, or it could be at the end, and the B could be first or middle or the end. So you're going to have figure out a way to represent that. And it says at least one occurrence, so it could be in other orders too, with the A's and B's and other places. So I'm going to have to let you figure that out. Now, one thing that comes up here, all strings of length 3 that are palindromic. Palindromic just basically means it reads the same forwards as it does backwards. So in other words, if you have a string like AAA, that's palindromic because when you flip it around, it reads AAA when we flip it backwards. All strings of length less than 3 that are palindromic is the next one. So that would be a length 0 or 1 or 2. Part F was all strings exactly length 3 that are palindromic. G is all strings of length less than 3. So 0 symbols, 1 symbol, 2 symbols has to read the same forwards as it does backwards. All right, the second part of this, part 2, it changes the alphabet to the binary alphabet, just 0 and 1. All strings ending in 0, 1. And let me do one of these quickly as well. So all strings ending in 1, 1. So you might originally think, well, 1, 1. That string ends in 1, 1. But the problem with that way of thinking is, again, just like on the previous one, we can make these into a little bit easier to see ones. That's a 1. Those are pretty bad, but that's a 1, 1. Now, the question is, what can come before that 1, 1? And the answer to that is, well, it doesn't say. It just says it has to end in 1, 1, so that ends in 1, 1. But what can come before it? Anything that's in this alphabet. So what I would suggest here is we do something like this. We could say 0 or 1, and then we need to star that whole thing, but we can't just put a star up here because we need to have the 0 and the 1 together. So that's a parenthesis, that's a parenthesis, and then we're going to star this. I did a little better on the star there, but worse on the parenthesis. But so 0 or 1, that whole quantity star, followed by 1, 1. So now everybody should get at least 2 of these right. Now all strings not ending in 1, 1, that's a little more difficult because you have to, again, represent any, all, and only those strings within your language. So you might think, well, what are all the strings not ending in 1, 1? Well, you might put some thinking into that and say any string that's part of this alphabet that does not end in 1, 1. What does that look like? Okay, all strings containing an even number of zeros. It doesn't say what order they're in, it just says there's an even number. It doesn't say how many ones there are, it just says even number of zeros. Now the complement of the previous language means all strings that are part of this should be sigma star. The universal set is alphabet star. So all strings over this alphabet that do not contain an even number of zeros. So you'll have to think through that one. All strings containing an even number of symbols, again, over this alphabet. All strings containing the substring 0, 1, 0, all strings containing the subsequence 0, 1, 0. So you're going to have to do some thinking about these ones. And I always thought these were kind of fun. They're like kind of like little logic puzzles to figure out how do I make a regular expression that gives me any, all, and only those strings in that language. All right, now part 3 is the language now, or the alphabet now switches to A and B, so only A and B. And this time I use set formers here. So let me quickly kind of give a description of what's going on. Let's look at A, since that one looks a little complicated. So this is saying all strings L are all strings in the form V, W, V. Now an important thing to notice about this is this first part, this V here, is the same as the V there. In other words, the first part of the string has to match the last part of the string. Those are the same V. And V in this case has to be length of 2 and entirely composed of A's and B's. So in other words, the length of that, this is a 2, meaning the first 2 characters have to match the last 2 characters and only be A's and B's. So in other words, if the front is A, at the end has to be AA. Now what can come between them? Well, W is just 0 or more A's and B's, so W is just 0 or more A's. So this is saying I have 2 symbols at the front that match the 2 symbols at the back, and between them are 0 or more A's and B's. So you have to figure out how to do that. Now let's look at the second one. The second one is saying we have a string of A's that are n symbols long, or that is n symbols long, followed by a string of B's that is n symbols long, and the number of A's has to be greater than or equal to 1. The number of B's has to be greater than or equal to 1. But if I add the number of A's and the number of B's together, it'll be less than or equal to 3. So in other words, this will always be 3 or less symbols, but I have to have at least one A and at least one B. And the A group of A's has to come first. The group of B's has to come second. The next one is similar. We have a string of A's followed by a string of B's. But if I multiply the number of A's times the number of B's, I get the number 6. So you have to think about, well, how many things can I multiply together to get 6 and represent all of those possibilities there. The next one says I have something that starts with an A and ends with an A, and between the 2 A's I have a string of B's that is 3 or more in length, and then this W is just 1 or more A's and B's after that B before the final A. The last 2, all strings W, obviously over this alphabet, such that the length is odd. All strings W, such that the length of it mod 4 is 0. Now, what does that mean that the length mod 4 is 0? Remember what modulus does? It gives you the remainder of a division. So if modding by 4 gives you 0, that means it's the length is evenly divisible by 4. So in other words, the length is going to be a multiple of 4 in all of the strings in this that are over that thing. Okay, so that's pretty much what you're going to be doing for this lab. So let me switch back to the presentation quickly. Okay, so we took a look at the lab, and the next thing that I want to do here is essentially that's a little bit of a shorter lecture today than the lecture time. So what I want you to do is work on that lab, try to get that done and submit it. And what I would suggest doing to work on that lab is, I guess there are a couple ways that I would suggest working on that. One of them would be, I would say, download that PDF, copy and paste it to some word processor document, type in your answers into that, into each of the things, and then save that off as a PDF and submit it on Blackboard when you do that. So that's all for today. Go ahead and work on that assignment. See if you can come up with those languages. And again, you might want to go back through and look at them after you've gone through it once, because you got to kind of get yourself used to looking at those regular expressions and being able to envision what it is that language looks like that it's creating. And again, the key there is making sure that you cover all of the strings that fit that description, but don't accidentally have other ones that don't fit that description in there. Okay, so work on that, and make sure to observe the due date on that. And next class, we are going to do something a little more interesting with those regular expressions. Remember how we said they were like algebra? Well, one of the cool things about algebraic expressions is you can manipulate them. They're algebraic properties, like the associative properties and commutative properties. Well, the cool thing about regular expressions is now we have this kind of formal methodology for representing them. We can manipulate those using algebraic properties just like we can with algebra expressions. So we're going to take a little bit of time next class looking at those and doing that. Also, keep an eye out for the quiz from the previous class content. Make sure that you keep up with that and get that done. And as always, if you have any questions, shoot me a text message, send me an email, give me a phone call, Facebook Messenger, whatever. But if you need something quickly, probably text message is the best way to get a hold of me. If you need something that requires a more complex question where you need to write out an explanation and a longer question, probably email is a better way to go. But that's it for today. Everybody stay safe, work on the lab, and next time, algebraic properties of regular expressions.